That is Carl Brandon. Thank you. Here. Carl, yours is, that was, this is the one, right?
Yep.
I downloaded it yesterday, so it should
Okay.
be good. Slideshow. Are you wearing the, you need
No.
the thing. So I think that's supposed to get that. Let me turn it on. Do you also need it?
Yeah, or you could use the hand. You have a pointer,
Yes, so this is the pointer.
and to advance, this works too.
Forward
Okay.
and reverse. Try it if you want.
Yeah, I'll do it in a minute. Okay.
Okay.
So I'm Carl Brand. I'm here with my colleague Peter Chapin, and we're from Vermont Technical College. And we're going to talk a little bit about a software system that is being developed based on our experience with our first CubeSat. This picture is a picture of, first picture taken by our CubeSat of the north, whoops, wrong button here. This is the north coast of Western Australia, and I superimposed a picture of the CubeSat itself, which we'll see on the next slide. This is a 1U, 1 kilogram, 10 centimeter cube CubeSat. Here's a picture of the CubeSat before launch. It was launched on November 19th, 2013, and was in orbit for 2 years and 2 days and worked. We communicated with it a few hours before it re-entered, and some statistics here about it. We did 11,071 orbits of the Earth. Unfortunately, it burned up over the mid-Pacific, so nobody saw it. It was during daytime. We were hoping it would burn up over Vermont and be cooperative so we could see it, but that didn't happen. But it worked, so that was the important part. And Peter's going to talk a little bit about the development environment.
This is working? Yes, it is.
Yeah.
Yeah, I think so. All right. So I'm Peter Chapin, as Carl mentioned. And this is just a little bit about the environment that we're using for development these days. We are using Spark, which is a dialect of Ada. I'm going to say quite a bit about that in a little bit. We have 2 faculty, that would be myself and Carl, and we have 4 students, 2 master's students and 2 bachelor students in our software engineering program working on it. We're using VxWorks for a test platform, also Linux for a test platform for what we're doing. So I should say a few words about what we are doing, and right now we're primarily building a system that we call CubedOS, which is a little bit of a misnomer. It's really more of an application framework. And it is very similar in terms of its goals and intended scope, at least, to what CFS is about. So it's an environment that's intended to be reusable and allow, we call them modules instead of apps, but pluggable components for building flight software. We're using Spark instead of C, which allows us to do some formal verification on it. In particular, our goal is to formally show that the code is free of various classes of runtime errors, which I'll talk a little bit about in a bit. And that's a work in progress. So that's a summary of what we're trying to do. So this is a little bit of a picture of the system, of the architecture in very broad terms. Pretty common looking picture. We have hardware down at the bottom, some sort of hosting operating system, maybe a flight software tier, Windows for development purposes, whatever is down there. And then we take advantage of the Ada runtime environment for some of the services it provides, such as tasking services and such like that. And then there's our CubedOS application framework, and then the mission specific components, modules that get plugged into it. And these parts are written in Spark, and the rest is whatever it is. So this slide just kind of repeats a little bit about what I just had to say. We rely on the Ada runtime for certain services. I mentioned the tasking, file I/O, and such like that. And this says a little bit more about CubedOS and what we're trying to do with it. It's a message passing system for sending messages between modules. The idea is to provide services of interest to flight software. This is very similar to what CFS is doing. We basically are writing all of our stuff in Spark or Ada, but there's no reason why you couldn't interact with existing C libraries, since that is a doable thing. And the last point I mentioned before about how we're trying to use the Spark tools to verify it free of runtime errors. I'll get to that in a minute. Instead of apps or applications, as the CFS people will call them, we refer to them as modules. The modules pass messages among themselves by delivering them to mailboxes. Each module has its own mailbox. And then each module has a task which consumes the messages and processes them, all the modules executing asynchronously. It's all in a single address space right now, but I have a few things to say about how that might be different in the not too distant future. As far as the message data is concerned, the parameters of a message get encoded, and we're using XDR, which is a internet standard for this, and the XDR encoded messages are sent back and forth. Some of the code that is being used is library code, which is shared between modules. The modules are intended to be independent and basically don't interact with each other, with the exception of the fact that they can call into these library code blocks as well. This is the button I'm looking for. Here's a little graphic that tries to show you what I just said. Here's a bunch of mailboxes, a bunch of modules, one mailbox for each module. These are green arrows. I don't know if you can really see that color, but each module has a task that reads its mailbox only, and then it sends messages on these gray arrows to other modules as required by the application. All modules are treated equally in the sense that the system doesn't regard any of them as being higher level than the other, but that doesn't mean the software can't have a layered architecture. It just means that the layering is imposed by the programmer. So we have a number of sort of core modules that we've been developing, and these are, again, analogous to the various services provided by CFS, the core services. And some of these are more mature than others. But we have a tick generator module that produces housekeeping, timing services of one sort or another. A publish-subscribe service. So the message passing in CubedOS is point-to-point. So each message is delivered to only a single receiver. But we've layered on top of that the ability to publish messages to channels that other modules can subscribe to with the assistance of this additional component, this publish-subscribe server that handles that. This is a picture of a possible architecture for a sort of a sample mission. This is fairly generic in many respects, but it's inspired by some of the missions that we've talked about and worked on and thought about. Down here is CubedOS. Beneath this is the Ada runtime environment and the operating system and so forth. Sitting on top of that are modules. These boxes are all modules, with modules for the different hardware components, power and ADAX and some kind of ion thruster or something like that, whatever we need. Up here are sort of higher level modules that control the operation of the system, logging, telemetry, scheduling of command execution, file services, and so forth as required. And I think I'm going to turn it over a little bit to Carl again to say a few words about the spiral thrusting part.
Yeah, spiral thrusting is one of the things that we're including because it is a very useful functionality for CubeSat class deep space mission. If you're away from low Earth orbit, where you don't have the ability to have magnetorquers for dumping excess angular momentum from your momentum wheels, this is a technique that was developed at JPL, which is very clever. If you have a 2-axis control on a thruster, and there's a commercially available ion thruster from Busick that has this, you can tip the axis of the spacecraft by just a degree or degree and a half from the direction of flight and rotate that axis in a circle about once every 30 or 60 minutes. And that exposes all 3 axes of momentum in the spacecraft to the action of the thruster. And by appropriate timing of when you actuate the thruster, you cancel out the unwanted components and put the momentum component in where you want to dump momentum from the momentum wheel. And in a small spacecraft like a 6U CubeSat, which is one we've been looking at, you just don't have room for auxiliary thrusters that you would have in a larger spacecraft to take care of that functionality. So it makes it possible to have a deep space 6U CubeSat that can handle all of its momentum dumping capabilities. And so that's a significant piece of software that will be part of this. It's a fairly complicated algorithm, and one of our grad students is working on that for his master's thesis.
Yeah, so these next few slides more or less kind of go through some of the points that I've already made, so I'll probably just skip through them a little bit quicker. But this talks about the driver modules that would be at the sort of the bottom of the application, a module for handling state. And this is, again, a sample mission. We have some of these modules are fairly general purpose, and we're building them up to be used generically, and some of them are would have to be much more specialized, of course. And so we just have placeholders in what we've got so far, largely. Storage management, scheduling uplinked commands, and so forth. Logging information, telemetry, and so forth. And the spiral thrusting module that Carl mentioned that one of our students is working on to try to make that algorithm work well. Because message passing lends itself fairly well to distributed situations, it seemed natural to think about extending the architecture that I talked about earlier to the case where you have multiple spacecraft. And so we started thinking about that a little bit. And so this picture is intended to show at least different communication domains, as we're calling them, where there's the array of mailboxes in each domain, which is independent, potentially on different spacecraft, for instance, or perhaps two different communication domains within the same spacecraft, different processes on the host operating system, for example, or whatever else seems appropriate. The modules are down here, 1, 2, 3, 1, 2, 3. And then there's a router component. So the messages, instead of being sent directly to the mailboxes of the receiver, get sent to the router, and the router figures out what to do with them, transferring to the mailbox, or potentially doing some sort of whatever is required to communicate with the other domain, depending on where it's located and how that's set up. That's just a general idea behind that. This notion is in its formative stages. We haven't really done a lot of work on implementing this as yet, but it's on the short list of things to do. So this is some comments about how this would work, or how it might work. So the routing component could do local routing or transport to a different process within the same system or a different spacecraft potentially, maybe of use in CubeSat swarm situations. The underlying network communication pathway could be whatever is necessary. For example, delay-tolerant networking, disruption-tolerant networking, if that's an appropriate thing, or the internet, or whatever else seems necessary or necessary or desirable. So this also means that our messages end up with these triples for addresses. So the message goes to a certain domain given by a domain ID, and a certain module within that domain. Module IDs are scoped by the domain, so module 1 in one domain is different than module 1 in another domain, and each module knows about a certain collection of messages. So the addressing becomes sort of like that. Okay, so I want to say a few words about why we're using Spark and what Spark can do for us. So the Spark is, as I mentioned, a dialect of Ada, also a set of tools, or several tools, that can be used with the source code to analyze the source code statically, and can do a lot of things for you that are some of interest. So first of all, it can analyze the flow of information throughout the program and find all uses of uninitialized variables, all computed values that are ignored, such as error codes. So for example, it alerts you if you just ignore error codes. Data races, and I say all uses of alias data. Well, basically it disallows alias data, so that's how that's handled. It also can execute, uses an inference engine to prove, in a mathematical sense, freedom from various sorts of runtime errors. Here's a collection of a few things. So it shows statically, I want to emphasize that, no dynamic testing here, but it shows statically that all array bounds are in range, that there's no arithmetic overflow, that any declared constraints on the ranges of variables are in fact obeyed, just for instance. I have here, it says that it finds pointer errors, and the way it does that, currently at least, is by simply prohibiting pointers. And so as a result of that, you don't get these kind of problems, no dangling pointers, no double free, no nullity references, and so forth, because pointers just don't exist. And you might think, if you have a C background, how can you write a useful program without pointers? But in fact, that's not an impossible thing, because there are other features of Spark and Ada that allow reasonable designs even without pointers in many cases. It is true that you do have to make certain concessions at times, but basically you can get things done. The other thing you can do with Spark is you can embed into the program pre and post conditions and other assertions to try to explain the intended behavior of the software at a somewhat higher level. And then the Spark tools will try to prove, again in a mathematical sense, that all the post conditions are always satisfied, all the preconditions are satisfied, any other assertions that you include are all satisfied. And again, these are completely static. So there's no runtime overhead, no dynamic checks. As a matter of fact, once the Spark tools sign off on the program, it is reasonable and appropriate to compile the program without all the runtime checking removed, because the runtime checks can never fail, at least if the proofs are correct and everything works as it's supposed to. And so that's a good thing. So our goal is for the CubedOS infrastructure and the supporting modules to all be written in Spark and verified in the sense that I've described here, to be free of these errors. Okay, I believe this is something that you've got.
Yeah, so I wanted to talk about this a little bit. I chose to use Spark Ada on our first spacecraft. I've been involved with Ada since it started in 1980. The first release was 83, then 95, then 2005, and currently 2012, and Spark in 1995, 2005, and currently 2014 version. And the reason is this language is much more reliable than any other language. And this is a study that was done on the C-130J retrospectively by the British Ministry of Defense, and statistics they found are very interesting. Per 1,000 lines of code, C errors this is all software that was certified and delivered and operational. So in that they found the error rate for C was 97 per 1,000 lines of code, Ada was 25, and Spark Ada was 4. An enormous difference in error rate. And a newer project, Tokeneer, which was done for NSA, had an error rate of 0.4 per 1,000 lines of code. In addition, in the Tokeneer project, they showed the productivity, this is from start of the project to deliver to finished and tested code, was 38 lines of code per day. That fits very well with our experience with a student writing about 80% of the software on our first satellite. And in several pieces of literature I found they give comparable numbers of in the 10 to 12 lines of code per day for C. The reason for that is there's lots of errors that you create in C that you have to find and try to get rid of. And so you have an enormous productivity advantage. And I've asked people, well, why are you using C? So, well, our students come here and they know C. And our experience has been that if you take a student who doesn't know anything about Spark or Ada, it takes them about 2 weeks to become productive. And that's not very much time. And at the higher productivity rate, at the end of 3 weeks in competing with an experienced C programmer, they have caught up. And in a program of the size that we just talked about in the previous talk, which was the size of our program in our first satellite of about 10,000 lines of code, the C programmer would take 3.33 years and have 970 errors. The Spark Ada programmer would take 1.09 years and would have 4 errors. The difference is just enormous. It would make the difference between your thing operating or not operating. We were launched with our first satellite with 12 university satellites. 8 were never heard from. 2 had partial contact for a couple of days. 1 was definitely software errors. We're assuming the others were software errors. And 1 worked for 4 months. Ours worked for the full 2 years that we had. Using Spark would have saved their potentially fatal errors on the Boeing 787. Has 2 sets of errors, which they haven't fixed the software. They just have some operational requirements. And these are errors that would kill people in the aircraft. And a potentially fatal error was avoided by a backup computer on the Mars Science Laboratory. All of those would have been prevented by Spark.
Can I make a comment there?
Yeah.
One of the interesting things that I've been working with is if you combine C with the efforts that you have to take doing static analysis of C after the fact, and you combine that with, and you compare that effort to starting out with Ada, which in essence does the static analysis or limitation on it up front, you know, I personally started with the early ADAs, and it was so cumbersome, it probably shot itself in the foot. But I think it really has a future, and we have to revisit it.
Yeah. It's used in every airliner in the world and every air traffic control system for a reason. You know, computers crash, and the word crash and airliner we don't like to have near each other.
I have a few slides here just to give you a little bit of a feeling about the sort of things that Spark finds for us. And you know, there's a bunch of code here, but I'll try to call out the important parts and sort of be as direct about it as I can. So this is these examples are, I'll say, taken from the CubedOS code base. They've been a little bit massaged. They're sort of reduced a little so that they can be fit on a slide in a reasonable way. But here's a compressed procedure that takes a bunch of parameters in, including C here, which is a trivial compressor object. It doesn't actually do any compression, so this is an example of, you know, it just copies the data around. Down here, if you run this thing through the Spark tools, it complains about this addition, saying right up here that the overflow check might fail. It gives a a situation where that arises. You know, for example, and it's not easy to, it's easy to understand how this would be. If the operation count is already at the maximum possible value, and I add 1 to it, then you'll have an overflow. So in ADA, that would raise an exception. So that's a fairly simple thing, and you think, well, obviously that's going to be a potential issue, maybe. So why are we talking about it? So the point is that the Spark tools find these problems everywhere in the entire program. Every single arithmetic operation is checked, and if the tools can't prove that they can't overflow, then it will say, well, it might overflow here. And so it produces these messages about these that force you to go back and take a look at these situations. We have a continuous integration server that does all the flow analysis and proofs every night and produces a report. And the idea is that before we finally deliver our software, that should be clean, no problems.
The Boeing error that would have been a fatal, meaning killing everyone in the airliner, that was an overflow error that would have been prevented by Spark.
The other thing about this I think is interesting is that this is a simple thing, and you think, well, you know, anybody could see this, a code review could see this, testing potentially could see it. But this occurs in a lot of places, and people overlook this stuff because it's very easy to say, well, I'll deal with that later or whatever. But ultimately, this speaks to potential requirements. I mean, what's the situation here? I mean, how many operations are we supposed to allow here? Do the requirements say anything of use? Maybe they do, maybe they don't. To deal with this problem, we're going to have to do something like maybe change some data types or put a precondition on this that says that these things can't be too far along, or put a runtime check in ourselves with an if statement or something. And so there's a sort of a trickle-up effect where these very low-level issues end up impacting the implementation in other areas of the program, or the design of the program, or even the requirements of the program. And you start asking questions about what the requirements are. Maybe they're not as complete as you would like. Here's another similar example where the Spark tools point at this multiplication. What this is trying to do here is it's taking a time interval in seconds, converting it into milliseconds by multiplying by 1,000, and then it's trying to convert that result of that into an XDR unsigned. That's a 32-bit unsigned integer. And so it says, oh, the range check might fail because this product might be more than you can fit into a 32-bit integer. Again, another example of a fairly simple thing that's pretty easy to understand and to see when you're looking at it. But it also shows what I said before, how the tools will find every situation where this can arise, sort of stuff can arise, and force you to do something about it. And there's different things you could do. And again, it might trickle up to design or requirements conceivably. I mean, how much of an interval is really allowed here? Here's another example that is a little bit interesting. This is some code where it's encoding some data for the messages, and it complains about this last line here, and it says that the precondition might fail on this encode procedure. So you think, well, what's that look like? This is the declaration of the encode procedure, and down here after the word with are a bunch of aspects that describe various characteristics of this procedure. Here's the precondition, there's also a postcondition. And the precondition on this, we're using XDR as I mentioned, and XDR has a bunch of requirements about how the data gets packed into the arrays, it has to be aligned properly and so forth. And so we're saying that, you know, the position given here, which is the position within the array, has to be a multiple of 4, so on and so forth. This one down here, this length width padding and so forth, This is a statement that says that there has to be enough space in the array to hold whatever this incoming data is. And so what's going on with this, if I go back to the earlier one, is that the Spark tools are unable to prove that there's definitely enough space in the payload array to hold this incoming data. And the reason why I can't prove that is because there isn't, but it may not be. In particular, the message payload has to hold the encoded channel number and also the length. And so that takes up space in the payload, and there may not be enough space left to hold the entirety of this message data. And so it's possible that this precondition might, in fact, actually fail. So to deal with this, this is coming from a message going to the publish subscribe server, which has the property that it takes messages and packs them into other messages. And so the message that's being put, the inner message, might be, if it were maximally in size, it wouldn't fit into the outer message. So in order to deal with that, we're going to have to think about how we're doing that a little bit more clearly, and maybe put a limitation on the messages that can be transported through the publish subscribe server, which is a factor that we didn't really reflect on as deeply as we should have. And again, here's an example of how these errors can trickle up to design and higher levels of the implementation. So that's that slide. All right.
Some of those errors.
Sure.
There was a deep space project. I can't remember what it was. It might have been Deep Space One. I'm not sure which one it was, but it had an overflow. The requirement for the mission was met, but the mission was extended far beyond its lifetime, so that there was an overflow in simple time in the time counter. And that caused an exception, and in the exception routine, it released an event message which it time-stamped, which caused an event, an exception, which caused et cetera. So that's where it is right now. So it's interesting that you would have to think about those things with the aid of error messages, with just that +1 saying there will be an overflow on this enormous number.
Yeah.
And maybe that would make you aware that you actually have a time limit. If your mission is extended beyond its original required time, you will actually get that overflow.
Yeah. I say one thing on the Boeing 787, the serious error, they were keeping track of time, and no one thought about the fact that somebody might keep an aircraft plugged in on the ground for 8 months. It turns out if you keep it plugged in for 8 months, you overflow on something that's keeping track of time that doesn't even really need to be there. And it puts the generators, all 4 of them, in safe mode. So if you're flying at altitude, you have no power for a fly-by-wire aircraft and you crash, and there's no recovery to it.
So what airplane are you taking out?
The FAA said, make sure you turn the power off for 8 months. That's the cure. They didn't fix the software.
I think the Patriot missile system had a time issue on it too, where they were leaving it out so long that it was skewing the original data.
Because we're doing message passing, and the message passing, the parameters have to be serialized and deserialized for each message, so that we write these encoding and decoding subprograms for that, which earlier slide was a sample of one of those. That's a pain. So I have one of my students working on a tool, we call it XDR to OS3, which auto-generates these encoding and decoding packages. And this is just a sample of the language that we're using, which we're calling MXDR, so it's modified XDR, that declares the messages and their parameters. And the tool will take this fairly abbreviated description of the messages and output the encoding and decoding procedures in provable Spark. At least when it's finished, it will. That's when he gets his thesis. So that's what's going on with that. This is a little bit of code that kind of illustrates some of the things about the mailboxes. I won't dwell on this in detail. We do have a message priority concept, which we don't actually use for anything at the moment. But the idea would be that you'd be able to potentially at least send high priority messages around in the system and have them handled in a more timely fashion. But at the moment, there's certain technical reasons why that's a little tricky to do. I mentioned this before about how the CubedOS module communication is point-to-point, but we have a publish-subscribe server that tries to deal with that. As far as what we're trying to do, as I mentioned, our verification goal is to prove freedom from the flow errors. and also freedom from runtime errors, so that those things I mentioned before will not occur. No out-of-bounds array access, no arithmetic overflow, no out-of-range values, no division by zero, and so forth. No pointer, no null dereferences because there aren't any pointers. So that's how that works. As time allows, it would be nice if we were able to specify a more detailed pre and post conditions throughout the code base. We do have them in some places, and then get Spark to try to show higher level functional correctness than just the runtime errors. But that's sort of a second level goal. Did I skip something here? No. Okay. One of the issues we have is talk about trying to run out stack space, which could be a problem for memory. Because there's no dynamic memory allocation in Spark currently, it's relatively easy to get a handle on how much memory the program is going to use, and sure, you won't actually run out of it. But we do need to analyze the stack space. Ada Core has a tool for that we will be using coverage analysis for the testing purposes. And you'll note that testing can spend its time focused on things that the proving doesn't cover. So things that we can prove to be true with the tools, we can sort of be light on the testing. It saves testing time. But the tools also will say, well, I can't prove that this thing you said is necessarily true. We review the code. We think it's correct. So we focus our testing on that area to say, well, can we break it with testing? So that there's an interaction between proof and testing that's can be quite nice. The proving process can guide the tests, and that's a pretty useful thing. So there's more about testing there. And at a higher level, we have exploratory test programs that we run on our development system, where we take the modules, glue them together, and see how they behave. We also are running things under VxWorks on a computer that could be used on actual flight to sort of verify they behave properly in that environment. And then a full system with the sample mission, sort of a mock mission, if you will, that we can execute on the ground or in space at some point. And that is that. Any questions?
Yes.
I think we have somebody back here. Go ahead.
All right. Have you thought about other ways to encourage user adoption? I know a lot of formal systems are developing shims, so you don't have to develop the whole code in say, F# or in this case, Ada, or interoperability with a mixed CFS, CoreOS, CubedOS runtime?
Yeah, so that's an interesting question. So it is certainly possible to call into regular Ada from Spark. That's fairly simple because it's basically the same language. Spark's just a restriction. It is also possible to call C code from Spark or Ada with the Ada Core's tools. So that's not a big deal to do that. We have done that in the past in our earlier mission, actually. As far as interoperating with CFS goes, that's an interesting question. And actually, I was at the CFS workshop yesterday, and I was watching the talks, and I was thinking, I wonder if we can build a gateway that can translate CubedOS messages into SBN stuff, and then that fashion, communicate with the CFS instance as well as doing what we're doing. That would give you the possibility of taking an existing CFS system and then maybe use this system for the critical functionality that is verified, perhaps. I mean, that's an option. That's something that would be worth looking at. We haven't done so yet, but it's on the list now.
Yeah. So, can you talk to when you look in the pre and post conditions? Obviously, you can introduce similar types of errors in the pre and post conditions. Does Spark check the pre and post conditions also to see if those could cause an overflow or cause something? Or
the answer is yes, it does. That's the short answer. There's a little bit of a longer answer regarding the different modes in which it operates. When you compile the program, you can direct the compiler to not generate any code for the pre and post conditions. And then you can also direct the tools and the compiler and stuff to treat the pre and post conditions as mathematical so that the integers that they work with are unlimited and such. Seeing as how you're going to be removing them anyway, it doesn't matter.
That's the way to do it.
But you basically, yes.
Could you comment on the experience of students who are C Spark as their very first programming language?
Students who know C going into our project.
No, students who've never done any programming before.
Oh.
And this is their first.
I could actually tell you a little about that. I actually taught the first undergraduate ADA course in the world to students who didn't have any background in programming, and was no problem at all. And I have not taught C, but prior to that I had taught BASIC and I had taught Pascal. And ADA is very readable, and this was the early version of ADA, which is a little more difficult to do some things with than the current version of ADA, but it was not a problem at all. And then if you have some work.
It's very different than C.
Oh,
Don't get me wrong, I'm a huge
Yeah.
fan. I've got my Grady Bush book.
okay.
But because C is so flexible, I was wondering how did the students take to something that is so
They seem to it doesn't seem to be a problem. If you like it, one of the things they like is that their programs work.
well, yeah.
You know, that's a very, and I had a faculty member who took my course, and he was amazed because he had been teaching programming before, and he'd never had a program work the first time through the compiler.
What about the other concept of ADA that I really liked was rendezvous? Is that a concept
what?
that rendezvous between
Oh, yeah.
tasks? Are you using?
Oh, yeah,
Does
yeah.
it one exist and two? Are you using
Yes.
that?
So you're asking about a couple things. So let me just comment very briefly on what you said first. I've taught Ada and Spark to students who have a background in Java and C, which is what we usually use at Vermont Tech as in most of our classes. And it doesn't take them long to learn the basics of what we're doing. Sometimes they comment on the stringency of the language, but some students really don't like that, and they never really get into it. But some will get into it, and they'll start to appreciate that they're getting something for that, which is good. So to your point about the rendezvous and such, so Spark imposes some significant limitations on the concurrency features of Ada, and in particular, the rendezvous is not allowed in Spark. However, Spark does allow tasks and allows the protected objects, basically monitor-like constructs, which we are using in CubedOS. The mailboxes are protected objects. But the rendezvous we don't use it because it's not allowed in Spark. Back there. No, go ahead.
Question about messages. Is there a maximum message size in the architecture, or can messages be extremely large?
Yeah, it's a good question. So yes, there is a static bound on the size of messages. The message manager, which is the package that actually creates the mailboxes, is a generic unit. So the mission, the developers can specify what maximum message size they feel they need for that mission when that unit gets instantiated. But once it's decided upon, it's a fixed maximum size. So that's another consequence of the fact that Spark doesn't allow us to use dynamically allocated structures.
We'll take one last question because it is 15 minutes already over. So, okay.
I've got a couple of comments. One of them is you showed 3 places where you had something +1. One marked in an error as an error, 2 not. So the question is, what happens with false positives? Because that's been a bane of static analysis of code forever. How often do you get false positives? We didn't see any there. But there were a couple of expressions that had something +1 that were not marked. Is that because it was previously provable that there would not be an error? Okay, so you had an explicit bound on the value you were adding to, so you'd know that was okay. Something like that. Okay, the other part is the thing about restrictions. I learned C a long time ago. And what I like about it is exactly that freedom, because I realize that everything that goes wrong is my responsibility. And that just makes me more careful.
Yeah. It's not good when it kills people, though.
It's not a student thing.
No, even with professional, I mean, that Boeing stuff was not written by students.
So just to quickly comment on what you said before, because Ada allows you to declare subtypes of the integral of scalar types with bounded ranges, the tools can fairly readily prove freedom from overflow and such in many cases, where it might, so you see these expressions where you're adding numbers and subtracting, and the tools will say, oh yeah, this is all good because I know these values are limited to certain ranges. So the number of false positives you get is less than you might imagine that you would get. You certainly do get some, though, but that's sort of a necessity. Exactly, exactly. So, but anyway, so yes, and yeah, the freedom of that C provides is great, and it does give you a lot of flexibility in the design. But on the other hand, there's the benefit of being able to, get the verification.
Well, I was right, C minus minus anyway. You have it here.
All right, thank you very much. That was a great presentation.